In the previous lecture, we discussed methods for simulating samples of random variables on a computer. So, we talked about pseudo random number generators, that means deterministic algorithms which would help you to simulate random numbers which are distributed uniformly in 0 to 1, and subsequently based on methods of transformation or accept reject methods, we are able to simulate samples of scalar or vector random variables, Gaussian or non-Gaussian random variables, and we also discussed what happens if random variables are completely specified and what happens if they are partially specified. So, this is what we discussed in the previous lecture. So, now in the present lecture we will now consider how to extend these capabilities to simulate samples of random processes. Now, we will go back to the discussion that we had earlier on Fourier representation of a Gaussian random process. So, we start with a 0 mean stationary Gaussian random process, and we define in terms of random variables a n and b n as shown here. Suppose x of t is n equal to 1 to infinity a n cos omega n t plus b n sin omega n t, where omega n is n omega naught. We assume that this a n and b n are random variables, and a n is normal with mean 0 and standard deviation sigma n, b n is normal with mean 0 and standard deviation sigma n. A n a k are independent for n not equal to k, they are uncorrelated, they are Gaussian, therefore independent. Similarly, b n b k are independent for n not equal to k, and a n b k are independent for every n and k. So, now first let us deduce what are the properties of this random process. What will be the mean of this process? Expected value of x of t is, you have to take expectation inside, expected value of a n is 0, b n is 0, therefore expected value of x of t is 0. How about its covariance? Expected value of x of t and x of t plus tau. So, x of t is the first summation here, n equal to 1 a n cos omega n t plus b n sin omega n t. The second term, n equal to 1 to infinity a n cos omega n t plus tau plus b n sin omega n t plus tau. Now, this becomes a double summation, and if we expand and multiply and use the fact that these assumptions on mutual dependence of a n and b n, a k and a n b k etc., we can show that this autocovariance is indeed a function of only the time difference, and indeed we get r x x of tau as n equal to 1 to infinity sigma n square cos omega n tau. So, therefore, it follows that x of t is has 0 mean and covariance function which is function of tau, therefore, it is a wide sense stationary process. But since x of t is Gaussian, because a and b n are all Gaussian and we are doing a linear transformation on Gaussian random variables, x of t is also Gaussian, therefore, x of t is also strong sense stationary. Now, let us consider, we will start the argument from a slightly different direction now. Let us consider a power spectral density function which is given by n equal to 1 s omega n delta of omega minus omega n. Corresponding to this, I get a covariance function which is, let me call it as r tilde r x x tau, which is 1 by 2 pi and the corresponding transformation following the relationship between covariance and PSD, and we can show that r x x tilde is 1 by 2 pi n equal to 1 s omega n delta omega n cos omega n tau. Now, let us compare this with the autocovariance of x of t that we just now obtained. We had n equal to 1 sigma n square cos omega n tau, and in this case if I put s omega n delta omega n by 2 pi as sigma n square, you can see that the two representations are identical. Okay. So, that would mean if this is the target power spectral density function of x of t, we can discretize the power spectral density into some n intervals, and the area under this interval I call it as s omega n delta omega n, and if I consider now for each of these intervals corresponding to the two random variables a n and b n and use this representation, we can show that samples of x of t as n becomes large will be having power spectral density which is the continuous form of the specified power spectral density function. So, this gives us approach to simulate samples of Gaussian random processes, stationary, zero mean with specified power spectral density function. So, you start with the power spectral density function, discretize, and for each segment you define two random variables which are independent and have the variance given by this area under the PSD, and use that in this representation, and you will be able to produce a samples of x of t which has power spectral density as given here. So, let us see an example. Simulate samples of a zero mean stationary Gaussian random process with properties that S of omega is an, say, I have selected for illustration an exponential type of a Gaussian type of power spectral density function, which is this is almost similar to a Gaussian probability density function, except that it is now a PSD function. Its area under the curve need not be 1, it will be equal to the specified variance, and some numerical values I have provided for the parameters I and alpha which appear here. Now, x of t I will write it as I equal to 1 to n a n cos omega n t plus b n sin omega n t. So, I am actually discretizing the power spectral density function into each dot is a point where I have discretized, and the parameters used are, we are simulating this for about 5 seconds and I am retaining 120 terms, and omega naught is taken as 0.2513 radian per second. The omega max, since there are 120 points, is about 30 radian per second, and delta t, which will be a function of 1 by omega max, is 0.0419 seconds. So, I simulate 240 Gaussian random variables with their mean being 0 and variance obtained from the target power spectral density function. You have to find area under those small intervals and you have to assign them as standard variances to the each one of those 240 random variables. So, if I do that, one of the sample that I got is shown here, blue line. This is a sample and 1000 such samples were obtained and the ensemble mean and standard deviation were computed. So, you see here the target mean is 0 and the black line that you see hovering around 0 is the simulated mean, and this green line, the pink line is the target standard deviation, and the green line that is fluctuating about this is the simulated standard deviation. So, things look quite okay. And the probability distribution function with 1000 samples, blue is the simulation and red is the target. There is reasonable agreement. Again, we can do a hypothesis test to actually objectively assess whether that agreement is acceptable or not. And this is the ensemble of the time histories, all of them I have shown on the same graph. This is again characterless, but gives a visual impression of what we are simulating. Another example, we discussed this Kanai-Tajmi power spectral density models when we discussed models for earthquake ground accelerations. Suppose I want to simulate now samples of earthquake ground accelerations whose power spectral density function is given by the Kanai-Tajmi power spectral density function with some of these parameters I equal to 1, omega g is the ground natural frequency, eta g is the ground damping. So, the idea here is that the soil layer is underlying overlying a bedrock is modeled as a single degree freedom system with damping eta g and natural frequency omega g, and it is subjected to a white noise acceleration at the bedrock level, and the ground surface acceleration is modeled as output of this single degree freedom system in steady state to the white noise excitation applied at the bedrock level. So, the target power spectral density function is the blue line, the axis on y axis is shown on log scale and x axis is on linear scale here. So, after doing I think 5000 simulation, we were able to estimate the power spectral density from the data, and it is compared with the target, and again we see good agreement between the two. So, in a future lecture I will describe how to actually estimate power spectral density from data and what are the sampling distribution for power spectral density functions and how to test hypothesis, etc. We will do that later, but right now we will be happy with kind of a visual comparisons, and this at that level the results are satisfactory. This is a display of a few samples of the time histories, again to give a visual idea of how the samples look. we are simulating samples of stationary random processes for a chosen time length. This is an example where this is another example where the covariance function is a harmonically decaying exponentially decaying harmonic with certain parameter displayed here, and the target density function is Gaussian, and what is shown here is the results on probability distribution function. Blue is the simulation, red is the normal, which is the target, just as an illustration. This is for the same example, this is the autocovariance function. Its Fourier transform will give us a power spectral density function, and a one sided power spectral density function is shown here. Blue is the target and red is the simulations obtained using 500 samples. So, there will be fluctuations, sampling fluctuations that arises, we need to understand that. This is a result on probability distribution function. Again, there is comparisons are satisfactory. Some samples of x of t. Now, so simulation of a scalar Gaussian random process with which is stationary with 0 mean and a given autocovariance or equivalently the power spectral density function seems reasonably straightforward. Non-stationarity can be introduced by multiplying stationary processes by suitable envelopes. That is one of the common strategies used. We will discuss that later. But right now we will move on to the problem of simulating samples of scalar non-Gaussian random processes. The description of the random process here is limited to the power spectral density function or the covariance function, autocovariance function, and first order probability density function. So, here we are considering let x of t be a random process whose first order PDF and autocovariance functions are available. No further information about the process is taken to be available. X of t need not be stationary. So, the problem is how to simulate samples of x of t. So, what we define? We follow the Nathav's transformation method that I discussed in the previous lecture. So, first step is we remove the mean and divide by standard deviation, so that y of t has 0 mean and unit standard deviation. Now, we introduce a new random process z of t through the transformation phi of z of t is equal to py of y of t, where phi of this argument is probability distribution function of a normal random variable with 0 mean and unit standard deviation. The z of t is a 0 mean Gaussian random process with an unknown covariance matrix or the covariance function here. So, we follow the argument. We have shown in the previous lecture that as far as the first order probability distribution function is concerned, the properties are preserved. So, we need not have to go through that step again. So, samples of y of t can be simulated following this rule once samples of z of t are obtained. Now, I need the covariance function of z of t. So, what I know is the covariance of y of t. So, I will express this in terms of the covariance of z of t. This rho star t1 comma t2 is not known. What is known is here, this is known, this is unknown. So, as a prelude to the implementation of this method, we have to follow that approach that I described in the previous lecture. We know, although this is not known, we know that this lies between -1 and +1. The left hand side also, this rho xx is also takes values in -1 to +1. This is known, this is unknown. So, what we do is we find out the left hand side for various specified values of rho star from -1 to +1 and compute the corresponding rho, and among these computed values of rho there will be one value which is the target value. So, we will be able to find out the corresponding rho. Now, this step can be implemented. So, the steps involved in simulation would be solve for rho star t1 comma t2 and simulate z of t, and then simulate y of t using this rule, and then go back and simulate x of t by using this rule. Okay. So, the computational steps involved are quite tedious, but in principle it is doable. So, things work out become a bit simple if a process is stationary. So, indeed I start with the case of a stationary random process whose covariance is sigma square exponential minus alpha tau and parameters of that is given, and I want the density function to be uniformly distributed between minus 0.5 and plus 0.5. So, first we have to find out rho star and then do this transformation, Nathan's transformation, and some results are displayed here. Red is the target and blue is the simulation, and the agreement is quite satisfactory. Now, this is a target power spectral density function, which is actually the Fourier transform of this, which is something like sigma square alpha by alpha square omega square, something like that. So, that is displayed here. The red and the blue is the target and red is the simulated estimated one. They show quite a good agreement, and we are unable to distinguish the two curves on this plot, and this is obtained with 500 samples. These are few samples of x of t. Notice that is uniformly distributed between minus 0.5 to plus 0.5, and it has 0 mean, and if you compute the power spectral density function or autocovariance function, it will match with the target values, target for values that is specified in the statement of the problem. Same autocovariance function, but with slightly different numerical values, but now the density function is not uniform, it is Rayleigh. So, mean will not be 0, the samples will have non-zero mean, and the parameters are specified here. Sigma that appears in the definition of Px of x is 2. How do I simulate samples of this process? So, again we follow this Nathan's transformation method and go through that. Again, let me emphasize, this description of the random process is not a complete specification of the random process. We are only telling the marginal density function and a covariance function. If the process is Gaussian, this is adequate. The first order covariance is sufficient for characterizing the second order properties, and the first order property would give you the mean, second order is covariance, that is enough to completely specify Gaussian random process. But we are talking about non-Gaussian random processes. So, this is not a complete specification. So, we are able to simulate samples whose properties match with what has been specified, and other properties of this process we really do not know what it corresponds to. It is left to the implicit model that is contained in the Nathan's transformation. Now, this is the power spectral density function for the Rayleigh random process, and the power spectral density function is shown on a log scale to make the comparisons clearer, and again the agreement between target, which is blue, and simulation, which is red, is quite okay. These are samples of Rayleigh random variable and the PSD that we mentioned, that random process, and again we can see that mean of these samples are non-zero, it is oscillating about some non-zero value, which is what we should be expecting for this model. Now, scalar random processes we are able to simulate. Gaussian we have discussed, target power spectral density or target covariance we are able to match, and for scalar non-Gaussian, the target first order PDF and the specified PSD or autocovariance we are able to match. Now, how about vector Gaussian random processes? So, to illustrate that, let us consider two random processes x of t and y of t. This is specified to be jointly stationary and they have 0 mean. So, the covariance, autocovariance and cross covariance functions completely specify the random process. So, the autocovariance of x of t is expected value of x of t into x of t plus tau, which is Rxx tau. Similarly, Ryy of tau is defined like this. Rxy of tau is the cross covariance function between x of t and y of t, which is expected value of x of t and y of t plus tau. Now, let us look at Rxy of tau. This is x of t into y of t plus tau. So, this is actually we can this is equal to y of t plus tau into x of t. Therefore, this should be equal to y of t plus tau into x of t, and this is nothing but our y Yx of minus tau. So, Rxy of tau is Ryx of minus tau. So, it is not a symmetric function, but there exists certain skew symmetry of this kind. Now, Rxy of tau is x of t into y of t plus tau, but this is not equal to y of t into x of t plus tau. Therefore, Rxy of tau is not same as Ry of x of tau. Okay. So, the R of tau is specified in terms of these functions. It is not symmetric, but there exists certain relationship between the two. Okay. Now, how about the corresponding descriptions in frequency domain? So, the Fourier transform pair of Rxx and Sxx are displayed here. The Rxx expressed in terms of Sxx and Sxx expressed in terms of Rxx. So, similarly, Rxy is shown here. Now, Ryx of tau we can write in this form and define Syx of omega, and since Rxy of tau is not symmetric, the corresponding power spectral density function will be complex valued and it has a real part and a imaginary part. So, we can show that since Rxy of tau is Ryx of minus tau, it follows that Sxy of omega is same as conjugate of Syx of omega. So, these relations exist, they are not 4 independent functions, but they are not symmetric either. So, there is a interdependence between the 4 quantities in frequency and time domains. Okay, let us examine this cross covariance and cross power spectral density function slightly greater detail. So, Sxy of omega is gamma xy of omega plus I delta xy of omega. Now, substitute this into the definition of Rxy of tau and I get this gamma plus I delta, and for e raised to minus I omega t I will write it as cos omega t minus I sin omega t. I can separate real and imaginary parts. Now, although Sxy of omega is complex valued, Rxy of tau is real valued. So, that would mean the imaginary part of this must be equal to 0. Therefore, this second integral must be 0. From this it follows that gamma xy of omega is a even function and delta xy of omega is an odd function. That ensures that Rxy of tau is real valued. So, this is a summary of the relationship between Rxy and gamma and delta, and we can use that property and write Rxy of tau as 0 to infinity 1 by pi now, not minus infinity to plus infinity. See, gamma xy is even, cos is even, so the product is even. This is odd, sine is odd, so odd into odd is even. So, both this integrand here is even, therefore, I can write it as 2 into 1 by pi 0 to infinity. Okay. Now, the various definitions of power spectral density function in terms of an expectation of a truncated Fourier transform, this is well known, we have already studied this, and based on this we can write the matrix of power spectral density functions, and Sxy of omega and Syx of omega are not the same, but nevertheless they are related through this relation that Sxy of omega is S star Yx of omega. Okay. Now, let us do start with Fourier representation for x of t and y of t. I will introduce for x of t 2 families of random variables a n and b n, for y of t 2 families c k and d k. Now, a n and b n, see the x of t is stationary, y of t is stationary, viewed as a scalar random process. So, the a n, whatever expectations, whatever conditions we impose on a n and b n when we are representing x of t will now must continue to apply. That would mean a n is normal, 0 mean and sigma x n, b n is similarly 0 mean, sigma x n standard deviation. A n a k are independent for n not equal to k, b n b k are independent for n not equal to k, and a n b k are independent for all n and k. So, x of t as far as a scalar random process is concerned, it has 0 mean and its autocovariance is given by this. So, this is a stationary random process, this we have seen. The same logic can be used on y of t, and we can show that Cn is normal, 0 means sigma yn is standard deviation, and so on and so forth, and expected value of y of t is 0, covariance of y of t is n equal to 1 sigma yn square cos omega n. So, this sigma xn square and sigma yn square are to be obtained from discretized version of auto power spectral density function of x and y respectively. So, that we have already seen. Now, what is now remains to be addressed is the properties, cross covariance properties and cross power spectral density function properties encapsulated in those functions. So, how do we deal with that? So, let us consider the expectation of x of t into y of t plus tau. So, for x of t I have this representation, for y of t I have this representation. I will use this and write it as the first term is this first summation and second term is the second summation where t is replaced by t plus tau. So, I run through these calculations, the product of summations become double summation, and I will now use the properties that we have encapsulated for an and bn, and what we will do now is I have not defined the properties between an and ck, how they are related, an and dk how they are related, bn and ck how they are related, and bn and dk how they are related, that we have not specified. So, what we will do is we will assume that an is independent of ck and dk if n is not equal to k. Similarly, bn is independent of ck and dk if n not equal to k, that we will but when n equal to k, I will impose certain restrictions on expectation of an, cn, an, dn, bn, cn and bn, dn, so that I will be able to simulate the properties contained in the cross covariance function. So, to do that, what I do here, first of all I want that the property that x and y are jointly stationary must be honored. So, if that has to be honored, the expected value of x of t into y of t plus tau must be a function of tau alone. So, for that to happen, if I take now expected value of a and ck is sigma ac n delta n k, this is Kronecker delta which is equal to 1 if n equal to k, otherwise it is 0. And similarly, if I place restrictions on a and dk, expected value of a and dk, expected value of b and ck and so on and so forth, I can show that the expression for Rxy can be reduced, the double summation collapses into a single summation. Now, I will make further assumption that sigma acn is minus sigma bdn and sigma adn is minus sigma bcn. If I do that, I can show that Rxy of tau now becomes a function of tau alone. Okay. Now, I can select sigma acn and sigma adn to make sure that this representation actually corresponds to the target value of cross covariance functions. How do we do that? Now, we will consider now Rxx, Ryy, Rxy. This is 1, 2, 3 are the consequence of the assumed properties of a and b and c and dn for n from 1 to capital N. Sxx omega, if I consider Sxx omega given in this form, we have already seen that the corresponding autocovariance function matches with can be made to match with function of this form by selecting sigma xn square to be equal to Sxx omega n delta omega n divided by 2 pi. So, if I that means this is the target, and this is what happens if I use a series power spectral density that I mentioned just now, and these two can be made to agree among themselves if sigma xn square is taken to be this quantity. So, that Rxx tau becomes R tilde of Xx of tau. Now, similarly, Sy of omega I define in a series like this, the power spectral density functions, and if I select sigma yn square to be given by this, I can show that the Fourier transform of this, which is R tilde Yy of tau, will match with the target autocovariance of y. This is similar, exactly similar to what we did for x of t. How about Rxy? Rxy of tau is given by this, and by separating real and imaginary parts and honoring the fact that Rxy of tau is indeed real valued, I get this function. I already shown that the imaginary part is 0 and what is the implication of that on properties of gamma and delta. Now, if I now consider gamma to be a sequence like this and delta to be a sequence like this and select, of course, you corresponding to this sequence you can take a Fourier transform, and that is quite easy because we have direct delta functions, the integration is very straightforward. If I do that, the expression for the cross covariance function can be shown to be given by this form. It is again of the form some constant of n multiplied by cos omega and tau, constant function of n multiplied by sin omega and tau. Compare this with Rxy of tau, and that suggests that if I select sigma ACN to be this and sigma ADN to be this, the cross covariance R tilde xy and Rxy of tau match. So, I have now the recipe to simulate the vector Gaussian random process. So, summary, I use this Fourier representation for x of t, Fourier representation for y of t. This sigma xn that appears as standard deviation of an is obtained from PSD of x. Sigma yn and that appear in Cn and Dn is obtained from power spectral density of y of t, and sigma ACN and sigma ADN that appear in the description of properties between AN Cn, AN Dn, Bn Cn and Bn Dn is obtained from gamma and delta of your cross power spectral density function. So, the auto power spectral density function of x and y, the gamma and delta functions for corresponding to the cross power spectral density between x and y are given. So, from that I can always by discretizing them I can always get sigma xn, sigma yn, sigma ACN, sigma ADN and we are ready to use this series. Once we are able to simulate AN, BN, CN, DN according to this prescription, we will be able to simulate x and y. So, summary is this AN, BN, CN, DN are 4-dimensional normal random variables with 0 mean and covariance given by this. So, to implement the method we should be able to simulate samples of AN, BN, CN, DN according to this prescription. So, here again you need to do the calculation that I mentioned, namely you have to find the eigenvalues and eigenvectors of this and do the transformation and first in the standard normal space and then work backwards and get AN, BN, CN, DN, where all these parameters appearing here are expressed in terms of known properties of x of t and y of t. Okay. So, after that we get expression for Rxx, Ryy, Rxy which is quite satisfactory. Some more notes: expected value of x of t into y of t plus tau is Rxy of tau, and expected value of y of t plus tau into x of t is Ryx of minus tau, which is same as Rxy of tau. Now, if you consider expected value of y of t minus tau into x of t, which is Ryx of tau, this is same as Rxy of minus tau. So, all this you can verify. Now, in our calculation we got sigma xy of tau as sigma ACN cos omega and tau, sigma ADN sin omega and tau summed from 1 to n, which is not equal to Ryx of tau, which is Rxy of minus tau, because sin omega n of minus tau is minus of sigma ADN sin omega. So, things are okay. These are some simple checks on basic properties that we should expect from such representations. Now, I leave it as an exercise. This is a fairly, this can be a fairly long exercise, which can be accomplished if you write a computer program. So, as an illustration, we will consider simulation of spatially varying earthquake ground acceleration. Consider x of t and y of t to be two random processes representing ground accelerations in the horizontal direction at two stations separated by a distance dxy. That means, in the same event of an earthquake, I take 2 points on the earth surface and consider the ground acceleration in a given direction, and at one point I call it as x of t and another point it is y of t. We can take that x of t and y of t to be jointly stationary, Gaussian and 0 mean random processes. The auto PSD functions of x of t and y of t may be taken to be of the form S of omega is I into h1 of omega whole square and h2 of omega whole square. This is typical Kanai-Tajimi power spectral density function model, where h1 is given by the transfer function of the soil layer and h2 of omega is a artificial filter function which eliminates certain anomalies in the low frequency behavior of samples of displacements that is needed to make the model work well at low frequencies. So, the auto PSDs are specified. This is a well known Kanai-Tajimi power spectral density function model, and we introduce a coherency function, that is Sxy by Sx square root Sxx Syy to be given by this. This is a complex valued coherency function which depends on the distance between the two stations and the wave velocity and the frequency, and it is a complex valued function. So, from this you can actually get multiply this by the two power spectral density functions, you get the cross PSD function, and you can separate them into real and imaginary parts, you will get your gamma and delta. So, you are ready to launch your simulation. So, the problem on hand is to develop a computer code to simulate samples of x of t and y of t, and to facilitate that exercise, some numerical values I have suggested here. Ground natural frequency is 15.6 radian per second and so on and so forth. So, the exercise consists of simulating maybe say 5000 samples of x of t and y of t, and then follow it up by from that ensemble of time histories estimate the power spectral density function matrix and compare it with the target PSD matrix. So, this is quite an involved exercise. The second part of this exercise, namely estimating PSD matrix from data of vector realizations, is something that we need to consider later. At this stage we do not have, I have not discussed this yet, but it is a part of this exercise. Now, I have talked about pairs of random processes. We can generalize it to say 3 random processes or n random processes. So, this method seems to work out quite well for this. So, we use 3 Fourier representations, and I have now auto PSD for x, auto PSD for y, auto PSD for z, cross PSD between x and y, x and z and y and z. So, I have to now each one is a stationary random process. So, represent finding properties of an and bn is purely based on the property of PSDs of x, y and z for say an, bn, ck, dk, em, fm. But to find the cross properties between an, cn, an, en, etc., you have to bank on the cross power spectral density functions. So, you can specify all these properties as per the formulation that I have just now outlined, and in principle it should be possible to simulate samples of n dimensional Gaussian vector random processes. I have detailed the various properties that we need to use, and I leave that as an exercise for you to verify. How about multi-parameter random processes? For example, if you are modeling wind velocity on a say a chimney. So, the wind velocity varies in time, but also varies in space. So, I have a random process which is a function of x and t. So, in a 3-dimensional situation, this x can be x1, x2, x, y, z and t, like ocean waves and so on and so forth. But here I am considering a single random processes function of 2 parameters. Okay. This is a scalar situation. So, we can have vector situations also here. Instead of just velocity, you can model some other parameter like pressure or something like that. You have 2 quantities, but we will consider scalar case first. We will assume that this random field has 0 mean and it is homogeneous. Homogeneity of random field is synonymous or analogous to stationarity of a random process. That would mean expectation of f of x comma t into f of x plus psi plus t plus tau is a function of xi and tau. that is a stationarity property. And corresponding to the 2-dimensional autocovariance function, I can define a 2-dimensional power spectral density function. One of the parameter will correspond to time, other one to space. This is the wavelength, this is the frequency in radian per second, this will be wavelength per unit length. So, I can define the power spectral density function. So, now I can use a Fourier representation involving ANK, BNK, CNK, DNK and products of cos and sine functions evolving in sine and evolving in time and space. Okay. Now, these are 0 mean Gaussian random variables. I will adjust properties of these random variables to suit the properties of this specified power spectral density function. So, the problem on hand is to simulate samples of f of x comma t whose power spectral density function in lambda and omega space is given. It is, and the process is given to be Gaussian. So, we can set up the same logic, we can make all these things for n not equal to k etc. to be independent, and when for certain cases when n equal to r and k equal to s etc., we will adjust those parameters and take them to correspond to the value of the discretized version of the power spectral density function matrix, and we can show that the autocovariance from such a model and from a model which is purely based on discretized version of power spectral density function would match if this ANK, BNK are selected in a certain particular manner, and you can simulate samples. Now, an alternate approach for simulation of non-Gaussian random processes with prescribed power spectral density function. This is based on Markov process theory. So, let us consider this problem. Let x of t be a stationary Gaussian random process defined on an interval xl to xr. Let px of x be the first order probability density function, and let the PSD function for purpose of illustration I am taking it to be of this form. Now, I want to simulate the samples of x of t. Now, what I do is I consider a stochastic differential equation dx of t is minus alpha x dt plus d of x dbt. Now, this equation is such that the 2-time response of x of t can be evaluated, and we can in fact compute the autocovariance of the response process. The parameter alpha and this parameter d of x are unknowns. Although I have selected alpha to be same as this, it indeed turns out that those two will be the same, but the problem statement is as follows. Suppose this alpha is say alpha star. So, the drift and diffusion coefficients are unknown. Okay. For this problem, the steady state solution to the governing of Fokker-Planck equation is obtainable. First order equations I showed already that you can solve the Fokker-Planck equation in the steady state. Now, what I do is I demand that if I were to obtain the steady state solution of this equation on first order probability density function, it should match with this Px of x. And similarly, if I compute the power spectral density function in steady state, it should match with this. So, what is known here are the solutions of this problem. What is unknown are this alpha star and d of x. So, this is an inverse problem. Okay. So, now what we do is we demand that these solutions match with the target PSD and PDF. That means determine the drift and diffusion coefficients so that this becomes possible. That means we complying with the target PSD and PDF becomes possible. So, how do we do that? So, we can start by multiplying the first of the equations by x of t minus tau and take the ensemble average, and from this we get the equation for covariance function in steady state, and we can show that the covariance function is of the form a exponential minus alpha mod tau, and corresponding to that I have this power spectral density function. That means this alpha I should have written as alpha star, so imagine this is alpha star, this is alpha star, as far as PSD function is concerned, select alpha equal to alpha star. Then our target is on PSD is met. The target on first order probability density function is yet to be satisfied. Now what you should notice is that the diffusion coefficient d of x has no influence on PSD of x of t in this equation. Now let us consider now the governing Fokker-Planck equation. So dx of t is minus alpha x dt plus d of x dbt, and associated with that this is the governing Fokker-Planck equation. In the steady state dou p by dou t would be 0 and I get this reduced equation. So one of the solutions for this would be of this form, and indeed we can solve this. This is the first order ordinary linear differential equation and we can solve this. Here what is not known? Alpha is known because already I have solved for that. P of x is given, right? D of x is unknown. So this has to be viewed as an equation for d of x. That means for what value of d of x would P of x would be the solution to this problem. Do you follow? So it is an inverse argument. So if I do that and solve for d square of x, I get d square of x to be this. That means if I consider now a stochastic differential equation whose drift is alpha and diffusion coefficient is d square of x, square root of this is given by this, and simulate samples of x of t according to this rule, the samples in steady state would have this power spectral density and the target P of x as a probability distribution function. So that means we are the SD is tailor made to produce the requisite power spectral density function and first order probability density function. Okay, it is an inverse approach. Okay, so as an exercise you can consider producing samples of Rayleigh random process with this power spectral density function or uniform distribution. I leave it as an exercise, I will not be able to, I will not discuss the details. Now I would like to briefly introduce a new topic, what is known as variance reduction. So before that we can summarize what all we have done. We have developed methods for simulation of random variables, scalar, vector, Gaussian, non-Gaussian, completely specified, partially specified. Similarly, methods for simulation of samples of random processes, scalar Gaussian, scalar vector, scalar non-Gaussian, vector non-Gaussian with partial specifications, and also discussed briefly a method based on Markov process characteristics of the solutions. So as far as simulation tools are concerned, we seem to be having the requisite a good deal of tools already available with us. Now the problem of dynamic response characterization has to be addressed now. So what we have done is we have simulated samples of actions. Now we have to run them through the system dynamics and get the samples of the response and then be able to solve them and get properties of response characteristics. So one of the problem that arises there is known as variance reduction, and I will briefly explain this in the broader context of Monte Carlo simulations, and I will consider the problem of evaluation of a multidimensional integral given by integral Px of x dx over a region g of x less than or equal to 0. So this is a problem that arises in structural reliability analysis. So the details of this statement of the problem and its relation to problems in structural reliability is not of primary concern here. What is of concern here is the computational details of evaluation of this integral using Monte Carlo simulations. So I can now the region over which integration is being done appears as a limits of this integral. I can first make the limits as minus infinity to plus infinity by introducing an indicator function on g of x. This I of g of x is 1 whenever g of x is less than 0, otherwise it is 0. So I can write it as I of g of x Px of x dx. Now therefore Pf can be written as expected value of indicator of g of x. Okay. So therefore this integral formally I am writing it as an expectation. Now my problem is to estimate this through samples of using samples of x. So let theta be the estimator, I running from 1 to n, ai, I g f xi. Now, the mean value of theta is given by I running to 1 ai expected value of this, and this is known to be pf, and this is I equal to 1 to n ai. Now, if this summation is equal to 1, we get theta to be unbiased. Variance of theta, I can do a simple calculation and I can show that variance of theta is actually given by this equation I equal to 1 to n ai square pf into 1 minus pf. Now, ai's are still unselected. So, what we do? We select ai I equal to 1 to n such that the variance of theta is minimized subject to this constraint. That means, moment this equation, this constraint is satisfied, theta becomes unbiased estimator, and moment this optimization criteria is met, we get an unbiased estimator with minimum variance. So, we can solve for ai, and we have gone through this step in the discussion on estimator for the mean, and we can show that ak is 1 by k. These are the optimal values of the parameters a1, a2, a3, an, and the associated variance is given by square root p of 1 minus p of by n. So, this result is quite similar to what we did earlier. So, in characterizing the estimator for the mean. Now, let us look at this slightly more carefully. Now, look at the standard deviation, which is square root of the variance of the sampling distribution. We get it in this form, and the coefficient of variation can be defined as sigma by m, that is 1 by pf into this, and a slight rearrangement will show us that this coefficient of variation can be given as 1 divided by square root p of n, when pf is small, which is most of the cases the kind of problem that we are studying. Suppose the answer is in the range of 10 to the power of minus 5, and you are looking for coefficient of variation of 10%, that is accuracy with which you want to compute the value of the integral, then the number of samples needed becomes 10 to the power of 7. That means, you need 10 to the power of 7 samples to evaluate pf, where coefficient of variation is about 10%. This coefficient of variation can be viewed as some kind of an error. On the other hand, if coefficient of variation becomes 0.01, okay, and probability of this pf, which is probability of failure in structural reliability language, is of the order of 10 to the power of minus 5, the number of samples needed becomes 10 to the power of 9. Okay. Now, we can make few observations now. This variance of estimator, which is pf into 1 minus pf by n, is independent of size of the basic random variable x. X can be 1 dimensional, 10 dimensional, 100 dimensional. This expression is independent of that. This n is samples, not the dimension of x. If this variance is large, the utility of estimator becomes questionable, because our population parameter is deterministic and we are using a random variable to approximate a deterministic quantity, its variance should be as low as possible. So, larger variance means the answer is less acceptable. So, the question of reducing the variance is very important. So, how do we reduce the variance? You look at the expression for the variance, the n is in the denominator here. So, it appears that in order to reduce the variance of the estimator, we need to increase the sample size n. But is it the only approach? We can raise this question, can we reduce the variance of the estimator without increasing n? So, this problem is known as problem of variance reduction. Variance can be increased by increasing sample size, but are there any other ways of reducing the variance without increasing sample size? So, for a given value of n, instead of using this as my estimator, can I modify this estimator and reduce the variance? The sample size is fixed. Okay. So, this question is of considerable significance when we analyze the response, because if you are applying simulation methods for practical structures, if one run of computer simulation of dynamical behavior of the system takes about say 5 minutes of CPU, and you are evaluating probability of failure of the order of 10 to the power of minus 5 with coefficient of variation of say 0.01 as I was mentioning, you will need to run the computer code 10 to the power of 9 times. And if 5 minutes into 10 to the power of 9 is a hopelessly large amount of computational time, and that approach is unlikely to work. So, we need to develop some intelligent methods to reduce the variance, and that issue we will consider subsequently. So, at this point I just want to state what is the problem of variance reduction. So, at this stage we will close this lecture. In the next lecture we will consider questions on simulation of dynamical behavior of systems. We have now completed the problem of simulating samples of random variables and random processes, and these descriptions will be useful in characterizing the inputs and initial conditions to the say the dynamical system. And now the question of how does this ensemble of random variables and random processes transmit through the dynamics of the system and produce the response quantities of interest. So, we will address this question in the forthcoming